It's my pleasure to introduce Dr. Yudong Yao from Stevens Institute of Technology. He'll be presenting updates on the research task ART-009 on intelligent defense systems. And with that, I turn it over to you, Dr. Yao.
Okay, thank you very much, Tyler. Hi, everybody. Thank you for joining this event and listen to this presentation. Okay, so the task is ART-009, and the title of the task is Intelligent Defense System. Sponsor is CCDC. It's a team project of 6 faculty. Project leader is Professor Victor Lawrence, and then we have myself, Yudong Yao. We have Professor Hongman, Professor Nigar Tavasolin, Professor Christina Komnichu, and Professor Serban Sabol. So it's fairly a big team for the project. Okay, so for this project, and our project title is Intelligent Defense System. You know, actually what we focus on is the armament system. So there's another way we call it is about intelligent armament systems. And then we have 6 faculty. We have 5 subtasks. It's like this. Number 1, AI and deep learning modules for multimodal learning and data fusion. So that's the first subtask. Second one is systems with unsupervised object discovery and description. And then the third subtask, multi-beam phase array Doppler radar for remote or multi-target detection. Number 4, cooperative monitoring for detecting adversarial communication. Number 5, high accuracy multi-round artillery firing, a control approach with terminal trajectory constraints. So that's we have the 5 subtasks. And then there's another way to see it and for the whole intelligent armament system. So that's our idea for the system of design, of research. And then we hope we have a good testbed environment for the whole system, the intelligent armament system. There are 5 main components from the task point of view. The first one, AI, machine learning, deep learning. We produce modules to run the whole intelligence. And then we have target detection to find the thing, target detection. Then want to know the thing, recognize the thing. That's the object identification. Then certainly we use a cooperative approach, use game theory for monitoring, and also a cooperative approach for control. So that's the 5 subtasks. Let me explain a little bit more about the ideas which each of the subtasks, so that we have very clear big picture of the whole project. AI, machine learning, deep learning are certainly very hot topic. Find many effective applications, right? People develop a new algorithm and use new data, but mostly for new applications, for various applications. So for this project, for this subtask, the highlight of this work is multimodal. Multimodal, which means the data source, multimodality. So we use those multimodal data to improve the learning performance. So that's the highlight of this topic, is multimodal learning. Okay, the target detection for this one is a faculty, Professor Nigar, is mostly use experimentation. It's use Doppler radar. She implemented the radar system and conducted experiments to see the performance detecting subjects, the individuals or other target. So that's the to see the hardware setup, what's the the parameters for the system, and then what's the performance of the detection. So that's this target detection task. For object identification, this one is another a learning related topic. It's use unique approach is unsupervised learning. Use unsupervised learning to identify any potential major objects in a scene, and then to identify the object. So clearly, those three tasks are very related to the armament system. Then the cooperative monitoring is about in the environment, certainly is the armament application environment, right? You need a surveillance monitoring the whole environment. So there will be a lot of sensors used for the environment. But the thing for this particular application is to find adversary entities, adversary communications. Those attack could be attack, right? So can be detected through the multiple sensors. And then furthermore, all those sensors, right? Some are effective, good sensor. There could be malicious sensors, so make the monitoring cooperation more challenging. And then therefore, that's through the cooperation to find the malicious sensor so that you achieve reliable monitoring. So that's the cooperative monitoring. Another cooperative thing for the control is this is a certainly again armament system is for the artillery firing. Instead of single firing is a multi-round instead of single round, multi-round firing. And then now you have a multiple entity, right? So how do they cooperative to have the maximum impact on the target? So that's the whole project, okay? And then there's another way I want to show you the relationship between the topics. Those are, all the 5 subtasks work together to support the intelligent armament system. And then somehow some of the output outcome from one subtask can support the next task. It's like this. For example, the deep learning for the multimodal learning, right? And then relates to the system discovery, identification, description. And then for this description task, use unsupervised learning. There's also weakly supervised learning could use the deep learning idea. And then you, with those ideas for the learning idea, will support the task 3 for the target detection. Also, those learning idea work with the collaborate with the game theory to support the cooperative monitoring. So that's the other task. And then certainly those learning control system support the subtask 5, multi-round artillery firing system. So that's we have the 5 subtasks and support the same goal to achieve intelligent armament system. And then somehow those subtasks are mutually related. Okay, so let me start for each. Now I will explain a little bit more detail for each of the subtasks. The first one is about the multimodal learning. Okay, so with regard to multimodal learning, what we need study, research, certainly we need to find the data sets. We need to use the data sets from database. Those data is multimodality data. It's like a multimodality means audio, video, text, and various the sensor device can capture from different source, and then they can combine together. Fusion methods, once you have all the data with a multi-data modality, how do you fuse the information? And then certainly to see the performance effectiveness of any idea, experiments to get performance. And for this subtask, the end goal output for the overall intelligent armament system is a set of toolbox: multimodal machine learning, multimodal deep learning. Yeah, as I explained already, the data modality, which means there are different types of information, like a sound, like a visual, like right, and the motion, like various type of information, and then the representation formats of the information. So that's the yeah, give you different modality. Modality is from different sources. They're really captured from different sources, and then the benefit is they are semantically correlated, so they provide the complementary information. So therefore, the learning performance are expected to be improved as compared to single modality data. And then this approach of multimodal learning widely used in many applications, widely used for many applications. Our, our purpose is to try to apply to use this technology for the unique application of armament system. So that's the intelligence come from the multimodal learning. And then here I mention the challenge, the lack of data. Typically for the AI, deep learning, the challenge always lack of data. But for here is even more so, because one is multimodality data is harder to get. And the second is also relates to the application domain, armament system in this application domain. And so, yeah, even more so for the lack of data. For our research-wise, a lot of experiments we can start from a generic approach, use a different variety of sources of data, and then in the future, when the armament system data available, we can apply. So it's not really bottleneck. We still can proceed with this line of research. Okay, so given the understanding and the expected performance advantage with multimodal learning, now we have the multimodal data. Then how do we put them together? So basically, there are three approaches. It's called early fusion, later fusion, and intermediate level fusion. The early fusion is we put things together at the very beginning, put the data together. As you can see from this diagram, put the data together directly. Okay, certainly the challenge of this is whether those data fit well at this level. So that's the thing. And then there's another one at a very later stage, later fusion, that's actually decision level fusion, almost like each modality just does its own job. So do the learning whole process and then reach a decision. Then the different decision then combine. So this is fairly common like ensemble learning and yeah, fairly straightforward. But this may not take full advantage of the multimodal data fusion capability, inherent strengths not. So therefore, with the deep learning, right, now we have this approach, intermediate level fusion. Basically is you have the data from different modality, extract the feature. Okay, now it's not the combined data, it's combine the feature. Of course, it may combine at a different stage. Once you combine the feature, then you have more enhanced feature, better representation, characterization of the object. Then you may achieve better performance. That's the idea. And then, okay, so those are the idea, the data, the algorithm idea. Now we need to do some experiments to see the performance. This is just, yeah, because as I said, the lack of data, we have to have something, right? So this is a UAV data set. UAV data set is the multimodality means one is they have the video, and then we divide into frames, right? So yeah, basically it's imaging frames. Certainly it's labeled because this is supervised learning. Then there's another dimension of the modality is sensor. Oh, the other thing, there's GPS information, IMU, inertial measurement unit. So there's other information inside. So we combine the imaging-based data modality and the other sensor modality. So that's the thing. For this task is to identify a set of objects, and then what need to do is create a bounding box so you can find something. So that's a job. You have a bounding box and then identify what's the object. Yeah. And also what's interesting is for the training data was here, right? Is certainly is like expert marked the thing, right? Is the work human labeled the thing. It even mentioned here the 3 worker will do the same thing, and if they all agree, then that's the label. So which means the learning data, the gold standard is very good, is very reliable. And then also this is just a quick mention of various parameters related to the sensor. I mean, we have the modality from the imaging frame, and also from the data sensor. Those are various things: the angle, altitude, the velocity, and everything the UAV have the sensor data. Okay. Anyhow, so the whole point is to see compare the single modality, which means uses the imaging certainly, right? Visual data only, with multimodal, which means combine the sensor data. That's the experiment. So this builds the model, this says the deep learning approach, and then this performance results. Anyhow, from this, the baseline result is 70.63%. So that's the performance results. 70.63 is not bad. And then that's for the single modality, uses the video frames. Okay, now the performance results. Okay, start the next step. Use the visual data. That's a video imaging frame plus the sensor data. We see the UAV carry sensor, also GPS. There's so many parameters, right? So therefore, this approach use the 2 set of data, go through the deep learning module, and then here extract the feature. And then the feature is, this is more like we mentioned the 3 type of data fusion. This is more like intermediate fusion. So the fusion and get the output. Those are different type of the the object. We consider 5 types of object for the classification, and then the deep learning model for each of modality also different. One they use CNN, the other one use a long short-term memory approach. What we interested is the performance results. Certainly these experiments, right, to do the how to build the model, and then how to build the model before and after concatenation of the features, data feature, and then those are the training process, the complexity issue described here. Okay, what we're waiting for is here, the performance results, right? Performance results when we combine the video frame with the sensor data, or performance results 71.60%. You know, it's you know, when we get the result, we are a little bit surprised. The improvement is so little, just about 1%. It's really I believe is how strong the performance effectiveness of the visual data. So the sensor data contribution is very little. But we do have another experiment for a very different application, just to try to show how much the performance improvement we can see when we have the multiple modality compared with single modality. For example, here we have 3 type of the modality data, right? And then the speech we have 50%. This is 64%. Another modality 50%. When we combine together, 70%. So this is more noticeable performance improvement. But yeah, so they just see the potential. As far as how do we use for the and for you, let me what I say. How do we apply this with the data structure, right? And we will be to get the performance improvement. Yeah, because we need the real armament system data to see the potential improvement. Okay. Okay. The other thing I do mentioned early that the challenge for the data, so the intelligent armament system data application, so those are the challenge issue. But in the future work, what we need to do is how do we do the security, privacy, preserving AI, including the blockchain technology, federated learning, right? So that even though those data is classified, but we can use the platform we build for the experimentation. So yeah, so this dark area is secure, and then we can use the open toolbox to do the experiment. Okay, so that's that. And then let me explain the next subtask from Professor Holman's team is for the object discovery and description. The highlight is use unsupervised learning. Okay, so and then for this project, right, this subtask, what's really trying to do is certainly use machine learning, right? The machine learning also here mentioned unsupervised learning, so there will be no user input, and then it's a lot to do with the probability scoring, with the scoring, so that we will see because there's so many potential object or object identification. So those called proposal. So the object proposal. And then how do we rank them? Use a probability score. And then with semantic label, there's certain relationship among them. So that's what's the thing. And then the way to do it, certainly, there's a feature identification part. So that's the user CNN. And then it the project to be able to give end-to-end, just give the results. You give a thing to analyze what object, what's the potential object. That's called the object proposal. And then again, unsupervised learning. So this is the highlight. Instead of you using solely entirely on the training data, it take advantage of the very well understood imaging characteristics so that to simplify the process, the performance observation through experiment. Here, try to say is because this subtask is use the unsupervised learning. Here, identify a few things of the weakness of supervised learning. So basically, is supervised learning very much based on the labeling of the data, and then it's without have a challenge, which is also true for the deep learning in general, right? How do we the interpretation always a challenge, but for here it's more gets into the reasoning to analysis from the unsupervised learning process instead of the traditional supervised learning without the reasoning, just do a mapping of object with text, vocabulary, label. And then for the Professor Holman's team in this project, right, it's kind of described in this block diagram. We can see from very input. So this input the imaging. So this input the imaging without a training, without the supervised learning, right? How to identify to see any object here? What's the object? So that's the task. Okay, as you can see, with this thing, like this looks like you can just use a deep learning, right? Use a deep learning, the high, media level feature, and then to identify potential object. So the rectangular block to highlight the potential objects. And then the other thing from the imaging input is to do edge map, because the object certainly have a clear edge, right? Use edge map. With the edge map idea, you can also have a potential the bounding box. And then from edge map, you have the proposals. That's the potential objects. They have the idea just from the edge map. Then you have those three input, combine them together, or all the squares, so many of them, those are potential proposals. So this is called the multi-view, so many of them, and then need to be ranking. That's a probability score. Because the probability of the strengths of each of the block are different. Rank them. Certainly you take the high end, right? And then you do not take all of them, so that you have reduction. You have reduction, that's the proposal reduction. So therefore you have fewer blocks. And then eventually you reach the point, the object discovery. You find something, and then what's the object? So that's described the idea. And then, as we say, that there's so many potential possible proposals, and then you need to rank them. There's a probability score. So that's the idea, the unique contribution of this subtask. As we mentioned earlier, the object proposal, the edge map, the box, and then there's multiple objects, and then the score, right? The score. Oh, the high score give to there's a match is between the the edge contour and the rectangular box. If they are more close, right, then the score be higher. In any case, the deformable shape score, that's what's introduced in this research, right? Use the scoring to each object box. And then, so the next few pages shows the experiment results, like all those pictures shows the red box, white box. Red box is ground truth. White box is the proposal with the highest score. Proposal with highest score is let's say is based on this algorithm. I believe this is the performance. Okay, so this is quite a good match, and then this looks a fairly good match. This fairly good match. The red, white here. This is certainly very good match. And another one, and you can see what's the ground truth. Ground truth, and then this is the top score proposal. Ground truth proposal match very well through. Oh, like here, this one is ground truth is here, the red, but the proposal there are quite a few, because the job for the object identification is to find the major objects. So depend on how do you evaluate the score, right, to determine how many major objects in this in any of the things. Also, there's one more. You have the ground truth identification. This match very well, and this is ground truth. The ground truth says the school bus here. There are a few more objects identified besides the school bus. Okay, those are the illustration of the performance results. And there's one more, and some do well. Typically when you see more complex things, there are more proposals. It's really hard to say, because when you have the red ground truth, really depend on what you define, depend on what you look for, right? Anyhow, so those white box achieved unsupervised learning methods. Okay, numerical wise, right? And the performance, we just seeing look at the few pictures to see a good match. Numerical performance here, one is the average detection accuracy. What's the detection accuracy? This experiment on this Pascal the imagings, right? Anyhow, there are so many different methods. This is a proposed method. This proposed method. Also, by the way, the proposed use unsupervised learning. For other methods, mostly you use supervised learning. So different approach. And then the way you count the success, the detection, it can be top 1, top 10 like this, right? And not converged. But anyhow, the performance is so good. It's a top performer, this proposed approach compared with everything. In terms of average detection accuracy. And then there's another thing, is because the imaging you have detected and the presence of the object, also localization issue, the localization rate, this again compared with so many different approach. Also for this experiment, it use a 20 class, right? Here say there is a cat, car, bus, but anyhow, the different object, and to see how good the localization rates. But then, and then those are the different proposals, the different methods. This work proposed method and then perform best in quite a few objects like a bike, boats, robots, but anyhow, but not all of them. Some other methods perform better in other object localization rates. So that's the performance results. But what's need to mention here is all other user supervised learning. This unsupervised learning, given that, so the work is really very interesting and significant. Anyhow, so the conclusion for this task is use unsupervised learning, and then also it does have a weakly supervised proposal ranking optimization process. And then the experiment certainly is very general natural imaging, right? And it certainly can be applied to in different application scenario, like our armament system. Okay, so this is very interesting results. And then this task is by Professor Nigar Tavasolin, is for the detection of target with Doppler radar. This is experimentation-based research. You can see the test bed, right? You can see the test bed. There's a transmit antenna, omnidirectional transmit antenna, and then this is circuits for the transmission receiving. And then this is a receive antenna. There's antenna array, receive antenna array. This is a beamforming network. It's a controller for the beamforming. So the first experiment set is a use a CW wave reader at 2.4 gigahertz. It forms 2 beams. Like for this one is to illustrate the effectiveness of this approach to detect a subject. So for example, the two body, 2 human, and then for the antenna array to find which direction, which the user, or what's the subject, the presence or not. The way to do it, they use a reference sensor. So basically, for this particular project, the user radar detecting the breathing process. This is called normal breathing. Breathe in, out, in, out. This is a hold breath. So that's certainly one human, right? And here, use those features to detect the presence. And then also, again, it uses a reference sensor which put on the body so that we can check the effectiveness of the radar detection. Yes, that's the idea. Very interesting. And then for this, generated a 2 beam, the page you can see, so that's a 2 beam range. There's a certain magnitude to see the variation because it is use magnitude, the difference from here to here, and the variation to identify the presence of the subject. Okay, so that was the CW wave radar. Another experiment, another setup use ultra-wideband reader. Ultra-wideband reader, this circuit board is here. You have a transmit antenna, receive antenna. This is circuits for the transmitter receiver control so that it will generate the beam. There's also under the computing device to do the signal processing. Certainly, the range for those commercial board is limited at this time. For example, if you follow FCC regulation, you can only allow the 5 to 10 meter, but the physical limitation is 50 meter. And because this ultra-wideband, there's a major limitation of power constraint. Okay, very quick. So what these experiments did, subject 1, subject 2, so all. And also there's another object through the ultra-wideband reader, it performs fairly good. So that's the 3 signal you receive from 3 subjects. And then this to analyze the match of the reference with the reader feedback so that identify the presence. And then also localization issues. Single subject experiment very location can all be detected. This is 2 subjects, and then some of them can be detected, differentiated, some get confused with another one. So this relates to the limitation of the number of antenna array. So therefore, so there's another experiment data is obstacle, because you have detected the subject, but what happens if blocked by the foam, the glass, the metal? So did a very good performance to see certainly with metal, or no, you cannot detect at all. Foam, no big deal. There's small impact on glass. So therefore, for the real application here, example would be the dry wall, the brick wall. So what's the range loss due to the obstacle? And then there's a future work, right? So this, what I say is the use the 2 antenna array, 2 separate antenna array. You can detect the not just subject, also the motion of the subject. You motion from here to here, you can do the tracking, the motion, the tracking. Okay, so let me be very quick, and then the few for the other 2 with the cooperative approach, right? Cooperative approach project is about the monitoring for adversarial communication. The basic idea is, and in environment like this one called intelligent armament system, right? So we have, if there's an adversarial target, and then we have so many sensors. The sensor cooperatively detect the presence of this target. And then, of course, each of the detection has performance issues. And then, even more so, the challenging, there might be malicious, compromised nodes. So this is through the cooperation game theory to detect the malicious user. So those other sensor will give improved, more reliable performance. Okay, and then so this approach is use game theory, and then the localization performance, accurate, fast, also save energy is also a major issue. So that's the because the sensor, right, is really limited energy. Okay, one more. This is also cooperative. Is about the multi-round. Or this Professor Serban Sabor. This is you see that's a multi-round from the source, certainly, right? Multi-round of artillery firing. How do they operate? The key point is there are multi-entities here. How do they cooperative together, exchange information so that the later round will follow the initial round to improve the performance? Because they are multi-round asynchronous, right? So the environment is different, the changing the environment. So the accuracy might be changing. So therefore, you need a real-time, on-the-fly cooperation. That's use the control theory, and then for to minimize the the deviation from the target, and very theoretical, interesting. It's a distributed control approach. Okay, so that's really the issue of the cooperation of multiple rounds through the distributed control and through the cooperation. And the future work will to see the learning methods and then if they can achieve better performance. So that's the okay. So yeah, that's a quick summary, and we can ask a question to discuss. Very quick summary. Basically, the whole task, intelligent armament system, right? What do? We use AI, machine learning, deep learning to do what? To detect if there's anything, to identify what's the thing, and then to monitor any bad thing, to control all those things. I should say object, detect the object, identify object, monitor the object, and then control the object. That's the last page. If any question, anybody. Thank you very much, everybody.
Thank you very much, Dr. Yao. There are no questions in the chat, and actually the session is at the time limit. So
okay.
I'd like to thank you again.
Thank you, Tyler. Thank you, everybody.